All right, let's peel back the curtain on the silent hero inside your computer, the operating system. We're going to talk about how it's basically a master juggler, keeping dozens of chaotic tasks running in what looks like perfect harmony.
I mean, have you ever really stopped to think about that? You're gaming, you've got a browser open with a million tabs, maybe some music playing, and it all just works. It seriously feels like magic, but it's not. It's a series of brilliant illusions, all managed by your OS. So, how does it pull it off?
So the first big idea here is what's known as the multitasking illusion. Here's the thing. On a single CPU core, your computer isn't really doing multiple things at the exact same time. What it's actually doing is switching between tasks so ridiculously fast. We're talking nanoseconds that to our slow human brains, it feels simultaneous. And the fundamental unit for every single one of those tasks is the process. The best way to think about a process is like a single chef working in a giant kitchen. Your web browser? That's one chef. Your game? That's another chef. Each one has their own recipe, that's the code, their own set of ingredients, that's their private memory space, and their own status. They could be actively cooking or running, they could be ready with everything chopped or ready, or they could be just waiting for the oven to free up, which is a waiting state. So how does the OS, the head chef in our kitchen, manage all these other chefs? It uses a set of core commands called system calls. Now, if you're a BTech student, you've probably seen these names pop up. A command like fork is basically like telling a chef to clone themselves to get a job done faster. Exit is how a chef cleans up their station and clocks out for the day. And wait is like one chef pausing to let another finish using, say, the only mixer before they can carry on. Okay, so having all these chefs in the kitchen is awesome for getting a lot of food out, but it also creates a massive new problem, right? What happens when two or more of them need to use the exact same part of the countertop, or the same salt shaker at the exact same time? This is where things can get really messy. It leads to something called a race condition. Imagine two processes try to update your bank balance at the same time. One wants to deposit 100, the other wants to withdraw 50. Depending on the exact unpredictable order they run in, you could end up with a completely wrong balance. It's pure chaos, where the result depends entirely on who wins the race. This whole issue has a formal name, the critical section problem. That critical section is just the piece of code that's touching the shared resource, like the bank balance. And any good solution to this has to guarantee three things, no exceptions. First, mutual exclusion. It's like a one-person at a time rule. Only one process in that critical section, period. Second, progress. If nobody's using the resource and someone wants in, you have to let them in. No pointless waiting. And third, bounded wait. You can't let a process starve. There has to be a limit on how many other processes can cut in line. So, the big question is, how does the OS actually enforce these rules? How does it stop the chaos and bring some order to the kitchen? Well, it acts like a very strict manager, giving programmers tools to make sure their processes play nicely together. Well, one of the first and most fundamental tools for this is something called a semaphore. The absolute easiest way to get it is to think of it like a token system. Imagine there's a ride at an amusement park that only 5 people can be on at a time. So there are 5 tokens. You need a token to get on. A semaphore is basically just a counter that keeps track of how many tokens are left. The first key operation is wait out. Your process walks up to the ride operator and says, "Hey, can I get a token?" This action subtracts 1 from the semaphore's counter. If the counter is still positive, great, you get a token and you get on the ride. But if that counter hits 0, it means all the tokens are gone, and your process has to stand in line and wait until someone else gets off. And signal is just the opposite. It's you returning the token when you're done with the ride. When your process finishes with a shared resource, it calls signal. This adds 1 back to the counter, and if there are other processes waiting in line, it tells one of them, "Hey, a spot just opened up. Here's a token. It's your turn." Now, semaphores are super powerful, but they have this one pretty big catch. They're kinda dumb. They put all the pressure on the programmer. If you accidentally forget to call signal after you're done, you've basically walked off with the token in your pocket, and now every other process that needs it is just gonna wait forever. This creates these insane bugs that are a nightmare to track down. And that danger, that fragility, is exactly why something better came along, the monitor.
A monitor is less like giving tokens to every programmer and more like building a secure room. All the shared stuff is locked inside. The only way to get to it is through specific, heavily guarded doors. These are the procedures. And the room itself makes sure only one process can be inside at any one time. It's just inherently safer. And just look at the difference here. It says it all. On the left, with semaphores, you have those wait and signal calls just floating around in your code. It's up to you to get every single one right. On the right, though, the monitor bundles it all up. The safety is built into the structure. It was a massive step up for writing reliable code. All right, so we've figured out how to keep our processes from crashing into each other. But the OS has another totally different, massive challenge to deal with: memory. How in the world does it fit all these different programs, each one screaming for its own space, into the limited physical RAM you actually have? The secret sauce here is this brilliant idea of separating two different kinds of addresses. You've got the logical address. This is the nice, tidy view of memory that your program sees. It gets to pretend it has this huge, clean, empty space all to itself. Then you've got the physical address. This is the messy reality of where stuff actually is on the physical RAM chips. And a special piece of hardware called the MMU, or Memory Management Unit, acts as a real-time translator between the program's dream and the hardware's reality. And that simple separation is what makes one of the most mind-blowing concepts in all of computing possible: virtual memory. It's the ultimate illusion. It creates this fantasy for each program that it has access to a gigantic, practically infinite amount of memory. This is literally how you can run a massive video game that's way bigger than the amount of RAM you have installed. So how does it pull off this magic trick? With a really clever strategy called demand paging. You can think of it as being productively lazy. Instead of loading a whole program into memory when you launch it, the OS says, nah, I'm only going to load the tiny little pieces or pages that you need right this second. The rest of it can just chill on the hard drive until it's actually called for. Which, of course, leads to the big question, right? What happens when your program tries to use a piece of its code or data that the OS was too lazy to load into RAM yet? This whole situation triggers something called a page fault. And it sounds like an error, but it's totally normal. It's part of the plan. The CPU basically says, whoa, I can't find this, and sends an alert, a trap, to the OS. The OS then jumps into action. It finds the needed page on the disk, finds an empty slot in RAM, yanks the page off the disk and shoves it into RAM, updates its internal map, and then tells the CPU, okay, try that instruction again. And this time, it works perfectly. So when you really step back and look at the whole picture, managing all these processes, preventing them from colliding, juggling this incredible memory illusion, the OS stops looking like just a manager. It starts to look a lot more like a symphony conductor. So let's do a quick flyby of everything we've just uncovered. We saw how processes create that powerful illusion of doing many things at once. We looked at the OS's basic toolkit with system calls like fork and exit. We learned how synchronization tools like semaphores and monitors stop the chaos. And finally, we saw how the magic of virtual memory and page faults lets us run huge programs on limited hardware. And really, it all boils down to this. The operating system is a master conductor. It takes the screeching violins and blaring trumpets of all these competing processes and somehow turns that potential chaos into a powerful, functional symphony. And that really leaves us with one last big question to chew on. These problems, managing shared resources, creating virtual spaces, we figured them out for single computers decades ago. But now, as we move into this wild future of IoT, with literally trillions of connected devices all trying to coordinate and share data, what's the next great critical section problem going to be? What's the next big synchronization challenge for humanity to solve? Something to think about.